Okay, so good morning, and we will continue our study of small oscillations. If you recall, what we did was to study fixed points, and of course, and expanded about the fixed point. So we are studying the motion in the neighborhood of a fixed point. So if the trajectory, is such that it remains in the neighborhood of the fixed point in time, we say it's stable. Okay, and and we expanded the Lagrangian to quadratic order, and so we noticed that we could write it as we could approximate it with the Lagrangian, which is T approx minus V approx, and theta here is Qi minus Q naught I. Okay, so this is the fixed point, and we introduce these matrices T and V, which are n by n. There are n degrees of freedom, so there are n by n matrices, symmetric matrices. Okay, and so the idea here, I mean, we have done it for a one-dimensional case, and but now we want to do it in generality, and so the idea is that we will study the behavior of this approximate Lagrangian, and yeah, is there some question? Okay, I guess not. Okay, so so these are the properties that we have, and so let's look at the Euler-Lagrange equations. Motion for L approx. Okay, so n by n symmetric matrices, they're constant. Okay, and the key point is that these matrices depend on the fixed point. A given system can have multiple fixed points, and these matrices will change depending on which fixed point that one is studying. Okay, so if you do this thing, so we get what we get is T. So dl, by doing dl by eta dot, we get T dot eta, and then when we differentiate this guy, we get this is equal to plus B. So I'm just putting this underline to remind you that this is the equation. Okay, this is a matrix version, so it's so T is an n by n matrix, n bar or eta dot is an n-dimensional column vector, so you multiply it to get a column vector. Okay, so these are n equations. Okay, and if you recall, T was just this matrix, which I call Tij, and V was second derivative evaluated at this thing, so we'll just call it Vij, its matrix elements. So this is the Hessian matrix. Okay, so it's the matrix of second derivatives evaluated at the fixed point. Okay, so this is what we have, and so we can write this equation again in components as Tij eta dot j, repeated indexes summed over, plus Vij eta equals 0. Is this clear? Okay, so these are linear equations, and people are not awake, I guess. It's d by dt of dl by d eta dot, right? I mean, that's what it is. So I forgot a double dot here. Okay, nobody pointed that out. Okay, so this is so these are the equations that we need to solve. let's look at this. So how does one solve? Okay, they're coupled, right? I mean, because this is the Hij is not necessarily diagonal. So how are we going to solve this? Okay, so let's do something. Let's say that eta bar of t is the following. And eta bar at some time 0 maybe e power I omega t. Okay, so let's just put this in as an answer, and then we get the column vector equation. I like that one. It just becomes so eta. So let's first do what is eta double dot of t will be minus omega square eta 0 e power I omega t. It's a standard method of solving for these equations. Of course, it's a second order equation. There will be two solutions, and we have to take linear combinations. All those things are true, but I'm just writing out something. Okay, so again, a question to you is that this appears to be a complex solution. What does that mean? Anybody? So here, I mean, this will be, what I'm trying to say here is that this will be complex. Of course, this is also complex, of course. What's the meaning of this? How do we make sense of this? Because these etas are supposed to be real degrees of freedom, and I've written something complex. So what does it mean? Anybody?
So these are like second order differential equations. So why are we allowing only one? Like we can also take e to the power minus I omega t. And then
That's
the
right.
linear combination can be real.
Yes, that's correct. Okay, so or we could write it in terms of sine and cosine, right? Sine omega t plus cosine omega t with arbitrary coefficients in front. Okay, so that's correct. So remark by what we really mean. Let's call this star. Eta of t will be real part of eta of 0 e power I omega t. Okay, and here what I want to emphasize is that this is complex. Okay, so if you expand this, so let's say eta of 0, let's say some eta real of 0 plus I eta imaginary of 0. Okay, these are all column vectors. Okay, we can do that, no? I can write that and plug it in here. Then eta of t becomes okay. So you can see that the complex way of doing this, the complex going to the complex basis, we are actually getting. So this is the most general solution. Actually. I don't need to take omega 2 minus omega. Okay, of course it will depend on value of omega, but that's right now. I mean, just is this point clear? So this is sometimes called the phasor method or whatever, you know. used quite often in solving wave equations and stuff like that. This is not a way. So this is what, and so now really here I should have, in this equation, I should have put real there. But the whole point is you forget about the real, you solve the whole equation. At the end of the day, we can go back and put real. Okay? So this is just a remark. Okay, so that's why I didn't do that, because it's a linear thing. In fact, you can even have, I mean, nobody said that eta of t should be real part. It could have been imaginary part also. That will also work. Okay? So, but convention is to choose the real part. Okay. So we go there and we need to, we plug it in there, and what we will get is a very nice equation, which will say something like this: minus omega square t plus this matrix V dot eta 0. Okay. So this is so what has happened is that so we get, so the differential equation in time now becomes an algebraic equation. Okay, so the key point here is eta bar of 0 shouldn't be 0, right? And it's boring. I mean, there's nothing. Of course, it's truly true. There's nothing happening. If eta equal to 0, that means you're at the fixed point. You're interested in eta bar of 0 being, something finite, non-zero. It can be infinitesimal, but it has to be non-zero. That's the key. So what is the equation that we should solve? What is the algebraic equation? Somebody? So we want to have non-trivial solutions, okay? And what is when will such a, so this is like n linear equations. When will they have a solution?
It should not be invertible, like minus omega square t plus v should not be invertible. So determinant is zero.
Determinant of minus omega square t plus v. Let me say this. Okay, so this is the condition. So this is a necessary condition. Okay, it's also sufficient. Okay, so in other words, we will look for all values of omega square such that the determinant vanishes. Okay, and so what is the order of this algebraic equation, or degree rather? T and V are n by n matrices.
N.
Okay, it's degree n in omega square. Okay, or omega power 2n, because only if squares come. So, okay, because of that. Okay, so this is a polynomial in omega square of degree capital N, sorry, that's what we've been using for degrees of freedom. Okay, so all these solutions omega 1 square, omega 2 square, omega n square. Okay, so one more nice remark is that if T were identity, and then what is the determinant condition is, then it looks like, then it becomes the standard eigenvalue problem, right, for V with the eigenvalue Lambda being what? Omega square, right? Come back here. Look at this equation. If it's just identity and you replace omega square by lambda, then what do you get? Get the standard equation. Okay, so but what we will do is because of this we will call. Okay, so we refer to the omega i's squares or omega i's as eigenvalues. Okay, and eigenvectors defined by what? Minus omega square, omega I square, t plus v acting on this vector eta I. We should solve for it. Okay. Is this clear? The notation nomenclature? We call, so you pick a value of, so you found n such values. Okay. And for each value, you can solve this equation and you will get a non-trivial solution. For omega square equal to omega I. So you can do this for I equal to 1, 2, up to 9. Is this point clear? Okay. So this is so we're able to solve these equations and we're getting the general solutions. And so now we can ask, before that, are there any questions, comments? Okay. So let's come back to the issue of stability. Okay. So what is stability? So suppose a fixed point is stable. Then what can we say about omega square, omega I square? A question to you guys, what do you think it is?
Real positive.
Okay, so omega I square would be greater than 0 for all I equal to 1. Okay, even if one of them is negative, okay, even if one of them is negative, the system is unstable in that direction. Okay. Okay. And okay, so I want to just give a definition. Okay, so we refer to the eigenvectors as normal modes. So let's use some other color. So eigenvectors have defined, just in analogy with this, as normal modes. Okay, so this is just a definition. Okay, so given a fixed point, we do the following now. I'm just repeating what we did. Okay, obtain L-approx. Next step is solve for omega I. Okay. Check their sign. And corresponding to each value of omega I determine the normal mode corresponding to it. Is this picture clear now? Okay. So here I just discussed two cases: omega I square greater than 0 and omega I square less than 0. Okay. What happens if omega I square is 0? What kind of equilibrium would you call that?
Neutral.
Neutral. Okay. It's not stable because you push it in that direction, it will just go to the new thing. And okay, so that's not quite stable. But this is only approximate. So if you go back to the full system, it could become stable, etc. But what I'm asking is, if L approximate were exact, then it is just neutral equilibrium. So really, that's what happens. Okay, good. Okay, so we have done all this in abstract, and you can see this captures exactly what we did in the 1D case, but it's now in higher dimensions. And one more thing to remember is that there are several things going on here. First thing is that both T and V need not be diagonal, okay? And further, this eta I need not be such that, it won't be a simple object like just one of them being non-zero, and the thing, it could switch on many, many different things. So let's do a very simple example. Okay, so let's spend some time and do something nice. Okay. So what we have is three masses connected by two identical springs. Of uncompressed length L. Okay. And further, motion is in one-dimensional. We could have other dimensions, but motion is restricted to one dimension. Okay, so, and let's say that the spring constants are K. And K is spring constant. Okay, so we need to choose, so how many degrees of freedom? First thing is? How many?
3.
3, right? And so let's just go ahead and choose coordinates. Let's say that this is x1, this is x2, and this is at x3. This is the instantaneous position of these places. I just drew them as big balls. You can think of them as point objects. We are not very interested. So these are the coordinates. So x1, x2, x3 are coordinates that we chose. Okay, so now question is, what is T for this system? Now I need help. What is the kinetic energy? No, this is not a trick question.
half mx1 dot square plus half capital mx2 dot square plus half little mx2 x3 dot square.
Thank you. What is the potential energy? Okay, so let's look at, there are two springs. Okay, so it'll be half k into the extension of the string, right? So half k into x2 minus x1. Okay, but it's x2 minus x1, and we should compare that with L, right? So x2 minus x1 will give you the length of the string, and from that you have to subtract L, right? Minus L or plus L. Okay. Plus half k into x3 minus x2 minus L. Is this correct? Is it minus L or plus L? I mean, okay. And what is the fixed? So we have now got L. L is t minus v. Now we need a fixed point. So what is the fixed point in this example? Okay, so let's choose one. x1 equal to 0. x2 better be L, right? Otherwise the spring is compressed. What should x3 be? 2L. Okay, and of course the corresponding momenta are 0, velocities are 0. These would be the initial conditions, right? This implicitly. Okay, so we have done this. This is a fixed point, and we want to study this. And now we have to, what is the next step? We have to extract the, so we have to define, say, eta 1 will be x1 minus 0, right? So that's just x1. Eta 2 is x2 minus its fixed point value, which is L. Eta 3 is this clear? Okay, and the good news here is that everything is quadratic if you look carefully. So there is no, I mean, non-linear terms which will come in the equations of motion. So we don't need to. So we need to now extract what are the matrices, right? So what is the matrix T? So you can see that eta 1 dot is x1 dot, eta 2 dot is x2 dot, eta 3 dot is x3 dot, right? Those two L's don't, L and 2L don't mean anything. So T is what? You agree? That's what we get from this. For V, we have to do some more work. So V is half k into x2 minus, so if you check carefully, it is just eta 2 minus eta 1 whole square plus half k eta 3 minus eta 2 whole square. All the L's cancel away, and this is what we get. So we expand. This is already quadratic, so we just need to expand this. And so we get half, okay, k into eta 1 square plus minus 2 eta 1 eta 2 plus eta 2 square. This will also give one more eta square. So I'll just okay, so when I expand this also I'll get one more eta square, so I'm just jumping one step. Okay, so we have to extract the matrix V now. So first let's look at the diagonal terms. Eta 1 square comes with 1, half is in the definition is gone, so it becomes k, this becomes 2k, and this becomes k. Off diagonal, eta 1, eta 2, so that will give us minus k, minus k. Okay, so think about it, this 2 will go away. There's nothing between eta 3, eta 1, so these are zeros. So minus k, which we can rewrite if you wish as k into 1 minus 1 minus 1 1 minus 1 minus 1 1 0. Is this fine? So we have got these equations. So now we need to solve for the eigenvalue. So first solve for the eigenvalues. Which is minus omega square t plus v that is 0. Okay, so let's do that. We need to do this. So the t is diagonal, right? So we get that of minus omega square into little m plus k and off diagonal terms come completely from only these sides. Minus k, minus k, minus k, minus k, 0, 0 should be, this should be 0. This is okay what I've written, but I can make mistakes.
Yes.
Okay, very good. Very good. So let's expand this determinant. Can you please work out and tell me what? I will also work out, of course. Okay, so this is good. So let's just expand this a little bit. Did I get my signs correct?
Yes, sir.
So there shouldn't be k square in the second term.
Why?
It's
Oh yeah,
minus
yeah. That's where some mistake was there. I couldn't see it. Now I can. So it is minus. I should multiply with this, right? Thank you. Now I am better, in good shape. Okay, so we can see now this is a common factor, so we just write it like this. Okay, and then this k, you can see that.
So there should be one more k.
K square.
Yes.
Okay, now we are fine. So what you see, what I want really is, to be honest, is this cancellation. Okay, this term should cancel with this. Okay, that's what I wanted. There should be some cancellation, and hopefully that's happening. Okay, so let's see how that goes. So expand this omega power 4 m this minus k omega square into what has happened? Oh, I've gone off the page, so I'll write it properly. Okay. There's some sign error. There's one more sign error. There is some sign error, right? Minus plus.
Minus.
There should be a minus.
Minus.
Yeah, thanks. That's a sign error. Sorry, I'm not so good at doing this. So minus 2k square. So now we see that these two terms cancel, which is very nice. So now we get something very pretty. This should 0 equal to this. So it is minus omega square m plus k into, now we can pull out one more factor of omega square omega square I can pull out, okay, and maybe I'll even pull out a k, but no, leave it that way. Okay, so this factorized neatly. Okay, we got very lucky because of several things. So what we get is that omega square, first term being 0, will be k by n. Second being 0 will give 0, and the last being 0 will be k by mu, where mu is something like mm. Okay, so we get 3 frequencies in this problem. Okay, so this is what we get. And so first thing we notice is that there is omega square equal to 0. Okay, and we would like to ask what is the normal mode corresponding to that. Okay, the next step is to obtain the normal modes. Okay, so of course, what does it say? You go ahead and you do this, right? Or minus omega square, put in the T matrix minus plus B matrix acting on eta I0 should be 0. We need to solve this. This is what we need to solve. But the 0 case is actually very, very intuitive and very, very simple. So I'll just write the answer, but I'll argue the following thing. So we can look at this fixed point. And we said that, we said that xi equal to 0, x2 equal to L, x3 equal to 2L was a fixed point. But we could have translated, right? We could have shifted x1, x2, x3 by any number, arbitrary number. What does that mean? There'll be no change in the potential energy will not change, right? If you shift all the 3 masses, say horizontally by the same amount, nothing will happen, right? There will be no change in potential energy, etc. So the fixed point doesn't change. So that's a neutral equilibrium. So this is the translational invariance in this problem. So it's for omega square equal to 0, okay, this is easy. Eta I of 0 should be just 1, 1, 1. Okay. If you want to normalize or something, you can put root 3 or whatever, but I'm not going to do that at this point. point. Okay, so is it clear that they're all shifted by the same amount? Okay, you can check this, check that it solves. Okay, the equation above equation above. Next one to consider is omega square equal to k by m, or it is omega equal to square root of k by m. Okay, what is the square root of k by m? So let's again come back and ask, we know something about this problem. If you give me a spring k, with spring constant k, and put a mass there, and you just make the mass oscillate, what is the frequency it would have? You're hanging a particle, a mass m, little m, from a spring with spring constant k. What is the natural frequency of that?
Root k by m.
Right, which is exactly this number. Correct? Okay, so let's go back and ask. Okay, so I'll draw some picture now. So I'll just say that this fellow, it just means so some epsilon times that. All of them are moved epsilon, epsilon, epsilon. This is the normal one. Okay, so now this is 1, 2, and 3. Mass 1, mass. Now I made them points. Okay, so now suppose we were in a situation where this point didn't move. Okay, and then but what we did was we moved this guy in this direction, and we moved this guy in this direction, epsilon, and this is 0. Okay, you will see that the both of them are identical masses, so they'll have the same frequency. They will both oscillate with same frequency k by m, but their displacements will continue to be always opposite. There will be some time when this will go inward, but at the same time this will go this way. So the middle guy too will not be moving. Okay, is this point clear? So again you can check. So I will write again for this. So we will call this eta 2 in our notation above. Eta, we'll call this eta 1 of 0 will be epsilon. Okay, 1, 0, minus 1. Again check this. Okay, is this point clear? There's intuition to this whole thing. Okay, now comes the last part, which is the last one needs some work, or maybe. What about omega square equal to k by mu, right? When mu was little m m plus 2n. So you need to work this out. Okay, what is the normal number? Okay, so let's now do this thing. Okay, so and there is also, so the thing is, so we need to, there is symmetry in the problem actually. Why? Because we chose the two outside guys to have the identical mass. Okay, so it's like inversion about the middle guy in some sense, middle mass. Okay, I'm just motivating what is going to happen. Okay, so but let's not. So what we need to do, actually, why should I even do that? Let's write whatever we got, right? What is the What was the matrix? This one, right? Okay, so let's write some. Okay, this should be 0. Okay, why? So now you can. So this is where I'm using. Actually, I should have put epsilon 1, epsilon 2, epsilon 3, or put some arbitrary factors in front. But I'm using the symmetry in the problem to choose something which will be orthogonal in some. Again, I have to explain what is orthogonality, but this is just a guess. You don't have to do this thing. Okay, so if you just go ahead and solve, what you will get is you solve for. Let's do it. This matrix is correct, no? Can you someone tell me?
Yes, sir.
It's okay, no? Okay, so let's even put. Let me be a little bit more cavalier. Call it B epsilon, maybe. So we have to determine A and B. So let's just do that. So first equation is minus omega 3 square m plus k into epsilon. So I just throw the epsilon 1 plus minus ka equal to 0, right? So this implies a equal to a equal to sorry, what am I writing there? Yeah, plus k. Is this fine? So this is what we get, and we can do the now. Let's do the third row. Third row. Do I want third row or this? Or which one is easier? Okay, let's do third row. Third row will give. Oh, what did I do? Okay, that's what we get, right? Third row. Okay, so you can actually compare these two equations. Okay, when do these two equations become identical? Doesn't matter what A is, we have got the expression for A. So you can see that I can take the difference of these things. This implies B equal to 1, which is what I claimed from symmetry. But okay, so we have solved for B, and let's write out A and put in values. So A is minus omega 3 square. Omega 3 square was what? K by mu, right? Okay. This is fine. Okay, and what was mu? I'm slightly bothered, but no, I know you need not be bothered. Why should I be bothered? Why am I bothered? By capital N, which is equal to, so you can see that this is, there's a cancellation, so we get minus of 1 plus little m by n. Hopefully I have not messed up. Is this okay? So again, this is again to be expected, in the sense that what is going to happen is that where is that picture? Here. So if both are moving in the same direction, this guy, to counter that, will will move in the opposite direction. That's what that minus sign is telling you. And so now what we are done with is that we've got all the modes, right? So we've got this mode. So we have obtained the 3 normal modes, and they are just proportional to 1, 1, 1, which was 0, and the other one was 1, 0, minus 1. This was omega square equal to k by n, and the last one was 1, 1, minus 1 plus little m by capital N. I'm worried there's some 2 factor or something, I don't know. Okay, it doesn't matter. This is please check this. Okay, check this particular number. Okay, so we have actually completely solved this problem, and this is neutral, and these are stable. So these are all greater than 0. Okay, so most general solution will be linear combinations of these 3 modes. Okay, so this model which I'm telling you is not, I don't think it's a very trivial model. It's actually a beautiful model. If you take a crystal, okay, crystals, what you can do is so a crystal consists say of ions or whatever, atoms, whatever. They're bound to each other, and you can, at least for small oscillations, you can approximate it by some kind of quadratic thing. So again, the crystal is stable, so all the omega squares will be positive except for one that would correspond to shifting the whole solid. So there'll always be this 1 omega square equal to 0, but then there will be Avogadro number of particles, and it's in 3 dimensions. So it will be 3 times Avogadro number of particles. That many modes will be there, but these will be collective modes. They even here you can see, right? You can see that here you can see that 2 of the degrees of freedom are participating. Here you can see all 3 are. So this is like a collective motion, right? So if you set it up in some eigen mode or a normal mode, it will remain in that mode. The other modes will not come. Okay, at least for small oscillations, that will happen. And coming back to that crystal, what you will observe is that there will be 3n minus 1 actually. If n is the number of particles or ions in that thing, there will be 3n minus 1 this thing. There will be what we will call a spectrum of the values of omega. There will be a huge number, and you will tend to take a continuum limit, and you will try to plot some curve as to what are the different values of omega that are allowed, etc. And this actually turns out to be a beautiful model for oscillatory modes of a crystal. Okay, in your StatMech course, you will deal with this, and so there you will appeal to this kind of computation. You are not going to sit there and do those computations, but you will be able to say something about the spectrum or some behavior of that spectrum which you can use. Okay, so you will draw some curve by taking some kind of continuum limit, and there will be a wide spectrum of values, allowed values of omega, etc. Okay, so so we'll maybe continue. Let's see if I have something more intelligent to say about small oscillations. Otherwise, we will stop here. I have to go back, and there are some formal things which I would have liked to do. Is what is the inner product? Why? How do we map this problem back to the standard eigenvalue problem? Otherwise, if I don't give a lecture, I'll write up some notes and share with you. Okay, so I'll stop here and pause for questions. And please check this factor of whether I got my A correct. Okay, I will also check.
Yes, sir. Like the defining of mu, there was the definition of mu. There was some like it was a bit incorrect.
Oh, it was 2 or something.
Yes, so the factor of 2 should be with small m, not capital M. Like even before this step, when you open the brackets, then it will be all right.
I'm happier now. This is what it should be, right? Even earlier there's a mistake. I mean, in my mind I had written that only. Yeah, this is where I defined mu, I think, first. That's okay now, right?
Yes, sir. Only like the third eigenvector will change, everything else.
Yeah. Only in the last step where I put where mu is, right? Thanks. Now we are okay? Fantastic. I have to correct here also, and then I'm done. Thank you. Okay, good. Any other questions or comments?
Sir, I wanted to this kind of reminded me of the time evolution in quantum mechanics, like we do same thing, like eigenvectors don't change. Like
yeah. I mean, it's the same idea because there, exactly. So there, what we do, it is similar to that because what are we doing there? The time dependence there is a first order. It's not second order in time. Okay, at least not. So it's d. There's I, which is don't worry, it's a complex equation. I d psi by dt you get, right? So there you say psi goes like e power I et, and then you solve for h. Yeah, it's exactly that. So you're solving for an eigenvalue equation for h. Here you're solving for this. Similarly, you solve for all the energies, right? And so similarly here you're solving for all the frequencies. So yeah. So in that sense, there h cross omega becomes the energy. Here it is just truly the oscillation mode. Okay. So yeah, the analogy is actually slightly imperfect, but a good one. The logic in terms of mathematical evaluation is the same. This is second order in time, and that is first order. Details. And here our things are real, and there it is complex. Okay, so good. Any other comment? A very nice comment. Okay, so let me stop recording.